In this video, we're going to look at displacement, velocity, and acceleration. We'll start with the definition of displacement. Displacement is the distance an object has moved from a particular point that we've set as zero, often the origin, over a period of time. The particular point that we've set as zero is referred to as our reference point. Displacement is given by the function s at t. Its units are m, and note that displacement is a change in position. It's not the same as the total distance traveled. So it's a change in the position with respect to the reference point. Let's move on to the next quantity. That's velocity, and velocity is the rate of change of displacement with respect to time. Since velocity is the rate of change of displacement, that makes it the first derivative of the displacement function, because it's going to be meters over seconds, and velocity has both magnitude and direction. The sign indicates the direction the object is traveling relative to the reference point. Also, don't confuse velocity with speed. Speed only has a magnitude, velocity has a directional component to it. All right, let's take a look at acceleration. Acceleration is the rate of change of velocity with respect to time. And since it's the rate of change of velocity, acceleration is the first derivative of velocity, which then makes it the second derivative of the position function or displacement function. Its units are meters per second squared, and acceleration describes the change in how fast an object is moving. It can have the same direction as velocity, and then if that's the case, if it's accelerating in the same direction as velocity, then the object is speeding up. But if acceleration is in the opposite direction of velocity, then the object is slowing down. Okay, let's keep moving on. Points of intervals and interest. For the time being, we're focusing on rectilinear, straight line motion, as opposed to 2D or 3D motion. It's sufficient for us to label one direction as positive and the other direction as negative. So that's how we're going to define these vector quantities. So one direction moving to the right will be positive, moving to the left is negative. Or if we say to the right of the reference point is positive, to the left of the reference point is negative. Okay, so what we're going to do is we're going to basically derive all these relationships of s at t, v at t, and a at t for these points of interest. So let's start right here and let's see, okay, when an object is at its reference point, what would be the position function? Well, the position function would be 0 if the object is at its reference point. When an object is at rest or stops moving, what is its velocity function? Its velocity function should be equal to 0 because it's at rest. The velocity is 0, which also means that the first derivative of the displacement function is equal to 0. Right, when an object changes direction, what exactly does that mean? So I'm going to draw out a little diagram for you to help maybe visualize what we're talking about here. So when an object changes direction, let's say that the object is going to the right, and then it changes direction and then goes to the left. Well, right at this instantaneous point, if it's changing direction, the velocity has to be 0, and then the velocity has to change sign. Because at this point right here, it's this instantaneous point, it stops moving, and the velocity goes from being positive to being negative. So let's write that out when it comes to those relationships. So the velocity has to be 0, and the velocity function must change sign. So in our case right here, it went from positive to negative. Alternatively, it could also go from negative to positive. When an object is moving towards the reference point, again, I'm going to provide some diagrams here to help visualize what we're talking about. So in this diagram right here, we have O as being the reference point, right? So that's actually 0, right? And this is the object right here. If it's moving towards the reference point, so you can see that the object P is moving toward the position, P is moving towards the reference point 0. The position is positive, but the velocity is negative because it's moving in the left direction. So we can see that they have different signs if it's moving towards the reference point. The position is to the right of the reference point, so it's positive. The velocity is negative because it's moving to the left. We can also have this case right here, where the object is in a position to the left of the reference point. So the position function would be, or the displacement function would be negative. and it's moving to the right, so its velocity would be positive. So when we look at our relationship with s at t and v at t, when an object is moving towards the reference point, what is that relationship between s at t and v at t? Well, that relationship would be as follows. S and t times v at t would have to yield a negative number if it's moving towards the reference point. Let's explain that again. The displacement function in the first case was positive because it was to the right of the reference point, but if it's moving towards the reference point, its velocity is negative because it's going towards the left. In this case right here, the position or displacement function was negative because it was to the left of the reference point, but because it's moving towards the reference point to the right, its velocity was positive, and so therefore when you multiply a positive and a negative number or a negative and a positive number, you will always get a negative number. And so that is the relationship of s and t and v at t when you are moving towards the reference point. Well, let's now look at the opposite, when an object is moving away from the reference point. And in this case right here, I'll provide both diagrams at the same time. So we can have an object that is to the right of the reference point and moving then further right. So that means that the displacement function or the position function is positive, and the velocity function will also be positive as well because it's moving to the right. The other case is if the object is to the left of the reference point, then the position function would be to the left and the velocity would be to the left, or velocity is to the left as well because it's moving in the leftward direction. So you would have negative and negative. Well, if we think about this relationship right here, what would be the product of s and t and v at t? Well, a positive times a positive makes a positive number, and a negative times a negative also makes a positive number. So our conclusion we can put right here. So if we're moving away from the reference point, the product of the position function or the displacement function times the velocity function should be a positive number, and we can see that from these products right here. Right, when an object is slowing down, so that means that its velocity is in one direction, but its acceleration is in the opposite direction. So I'll again give you guys a couple of diagrams here. So in this example, we have an object that is to the right of the reference point, and it's moving further right, so its velocity is positive because it's moving to the right. But if it's slowing down, then the acceleration has to be in the opposite direction. So the acceleration's got to be to the left, which makes it a negative number. So the velocity is positive and the acceleration is negative. You can probably think already what the second case is going to be. The second case would be as follows. If the position is to the left of the reference point, moving further left, the velocity is negative. But if it's slowing down, then the acceleration has to be in the opposite direction. So the acceleration is positive. Let's take a look at the product of these two functions. If the velocity times the acceleration, if velocity is positive times acceleration is negative, that's going to yield a negative number. Same thing right here. If velocity is negative and acceleration is positive, then that will yield a negative number. So our conclusion when an object is slowing down is as follows. Velocity times acceleration has to yield a negative number if the object is slowing down. All right, so what happens when an object is speeding up? Again, here I'll put up both diagrams at the same time, and then we can go to our conclusion pretty quickly. Okay, so if an object is speeding up, its velocity would be in one direction, and its acceleration has to be in the same direction if the object is speeding up. So in this case, the velocity would be positive because the object, and we'll say that's given by p, the object is to the right of the reference point, moving away from the reference point. So its velocity is positive, acceleration is positive. Alternatively, you could have an object that's to the left of the reference point, moving away from the reference point, so velocity is negative, and the acceleration is also negative if it's speeding up, because the acceleration is in the same direction as velocity. So you can probably imagine already what our conclusion is going to be with respect to the two functions, and it is as follows. Velocity times acceleration has to be greater than 0, so for the object to be speeding up. Okay, let's keep moving. An object can have positive or negative values for displacement, velocity, and acceleration. So let's take a look at this description in words. An object that is to the left of the reference point, traveling away from the reference point, let's just change that right there, that's from. Traveling away from the reference point and slowing down would have the following. So what you should do here is see if you can figure out what would be the values of s at t. So like, is it going to be positive or negative? What would the value for v at t be? Would it be positive or negative? And what would the value for acceleration function be? Would that be positive or negative as well? So take a second, pause the video, and see if you can figure those out for yourselves. Okay, well, if the object is to the left of the reference point, then its displacement function is going to be negative. If it's traveling away from the reference point, then the velocity function would also be negative if it's moving to the left. And then the acceleration function would have to be positive if it's slowing down. And we can verify that with all our products that we discussed up here in the note. But if it is traveling away from the reference point, then that means that both the position and the velocity function have to have the same sign. So in this case, if it's to the left of the reference point and moving away from the reference point, that means that the position function and the velocity function are both negative. And when you multiply them together, they make a positive number moving away. So that works out. If it's slowing down, that means that the acceleration function has to have the opposite sign of the velocity function. So if velocity is negative, then acceleration has to be positive, and their product has to be a negative number to indicate that it is slowing down. Again, that relationship we derive from first principles right here. So you go back and review that if you are finding that a bit confusing. Okay, let's take a look now. An object that is to the right of the reference point, traveling away from the reference point and slowing down. See if you can figure that one out as well. So I'll just pause the video and then we'll come back. Okay, so here you go. So if it's to the right of the reference point, the position or displacement function would be a positive value if it's to the right of the reference point. Now, if it's traveling away from the reference point, that means that the position function and the velocity function have to have the same sign. Let's see where we talked about that. Moving away from the reference point, the position function and the velocity function have to have the same sign for it to be moving away. Again, derived from first principles right here. So that means that your position function and velocity function both have to be positive. Now, if it's slowing down, that means that the acceleration function has to have the opposite sign of the velocity function. So in this case, the acceleration function would be negative because the velocity function is positive. Let's look at the next example right here. The displacement in meters of an object from a particular point after t minutes is given by the position function s at t is equal to 5 plus 6t minus t cubed. Determine the velocity and acceleration functions. Well, the first thing that we have to remember is that the velocity function is simply just the first derivative of the position function, and the acceleration function, that's just the first derivative of the velocity function, but it's also the second derivative of the position function. But what we'll do first is it's easier to just find the first derivative of the position function to get your velocity, and then once you have the velocity function, take the derivative of that to get your acceleration. So let's start with the velocity function. Take your first derivative of the position function and see if you can pause it and try and do that one on your own. And when we come back, we can check our answers. Okay, so here it is. So if you take the first derivative of 5, that's going to be 0. Take the first derivative of 6t, that's just 6. And take the derivative of negative t cubed, and that's negative 3t squared. You can see that you can factor out a negative 3, and you end up with this for the velocity function. Now, when finding the acceleration function, the easiest thing to do is take the derivative of this one right here. I'll just try and highlight it for you. This one right here is the easiest one to take the derivative of, as opposed to having to try and take the derivative of this one right here. Just go ahead and take the derivative of this because the derivative of 6 is 0, and the derivative of this would be negative 6t. And there we have it. Okay, so it says determine the object's position, velocity, and acceleration at t is equal to 2 minutes and interpret the results. So effectively, all we need to do is we need to find s at 2. So I'll write that out for you guys. We're going to just find s at 2. We're going to find v at 2. And we're going to find a at 2. Well, s at 2 is pretty straightforward. It's just 5 plus 6 times 2 minus 2 all cubed. And that is going to yield 9 meters. v at 2 is going to be negative 3, and I'll use the factored form for this, although I don't necessarily need to. Okay, and I get negative 6 meters per minute. Note that the position function is in meters. The time is given as t minutes, so the velocity is going to be meters per minute. Okay, and acceleration is at 2, so negative 6 times 2. And I get negative 12 meters per minute all squared. Okay, so let's take a look at these results and interpret them. So we can see right here that our position function is 9 meters, so it's positive. So it's starting to the right of the reference point. The velocity is negative, and it's negative 6 meters per minute. So that means that the object is moving to the left. Well, if it's starting to the right and moving to the left, it's moving towards the reference point. You'll also note that the velocity function and the acceleration function have the same sign. They're both negative, which means that the object is speeding up in the left direction. And if it's already heading left, that means that it is speeding up. It is accelerating. The overall object is accelerating in the left direction, so it's speeding up as opposed to slowing down because they have the same sign. So we're going to go ahead and write that conclusion. Okay, so therefore the object is 9 meters to the right of the reference point, moving toward the reference point at a speed of 6 meters per minute. Note that I'm writing speed. In this case, I'm just giving the magnitude of the velocity because I've indicated with words that it's moving towards the reference point at a speed of 6 meters per minute. The object is also speeding up at a rate of 12 meters per minute, all squared. And there we have it. Okay, so when does the object change direction? Well, let's just take a look at what we said happens when you have an object that changes direction. An object changes direction when velocity function is equal to 0 and the velocity changes sign. So if we take a look right here, this is my velocity function right here. So I'm going to set this one equal to 0 and find the values of t. All right, so you can go ahead and try that out on your own. Okay, so we take our velocity function and then we set it equal to 0. So I just rearranged the velocity function here so that my t squared came first with the negative coefficient right there. Set it equal to 0, move the 6 over, then divide by negative 3. So I get 2, and then I take the positive minus square root of t, but recognizing that t can only be positive, so I'm only taking the positive square root of t, and I get t is equal to approximately 1.41 minutes. So this one was pretty easy. I just had to find what t values make this velocity function equal to 0, and one of my t values was negative, so I know that I can just discard that value regardless. But let's see what this looks like in terms of a graph. Well, if we look at the velocity function, this right here is a parabola. So the velocity function is a parabolic function. It's a parabola that's opening down and has been shifted 6 units up. So I'm going to find the x-intercepts where x-intercepts being when v at t is equal to 0, and then also where it crosses the x-axis because v at t has to change signs. So I'm going to quickly graph that and see if that holds up. Okay, and there we have it. So we have a velocity function, which is a parabolic function. It's opening down because of the negative coefficient, and it's shifted 6 units up. Remember, I'm only taking the positive values, and I look at what t value makes this function equal to 0. Well, that t value is 1.41 minutes, and we can see that the velocity function is equal to 0 at that point, and it's changing sign because the velocity function is going from a positive value to a negative value. Okay, example 2, the displacement in meters of an object from a particular point after t seconds is given by the equation s at t is equal to 2t to the power 5/3 minus 5 times t to the power of 2 over 3. And the first thing it asks is, when does the object return to its initial position? Well, when it returns to its initial position, s at t has to be equal to 0. So that's what I need to solve for over here. I need to find when does s at t equal to 0. And this might be hard to see initially just looking at this function as it is. So the first thing that we're going to do is we're actually going to factor this function right here. And we factor this function as follows. We go s at t. We recognize that it has the common factor of t, and it has the common factor of t to the power of 2 over 3. So when factoring out, you look for common factors raised to the lowest possible exponent. In this case, the lowest possible exponent is 2 over 3. So it's t to the power of 2 over 3, and then open bracket 2t minus 5. If you're curious how you got this or how we got this, this is done by saying, remember that when you factor, you effectively are doing the following, okay? And so I'll just quickly do it over here. S at t is equal to, and then again, I'm going to factor out the t to the 2 over 3. So t to the 2 over 3, and then what effectively I'm doing is I'm saying 2t to the power of 5 over 3, but then I'm dividing by 2 to the t over 3. That's what happens when we factor. Okay. When we factor something out, we're saying we're going to divide all the terms within the bracket by that factor. And you'll see immediately that this right here will cancel, so we end up with our 5, right? And then the t to the 5 over 3 divided by t to the 2 over 3. Well, remember that if you are dividing two of the same bases, then you can subtract their exponents. So 5 over 3 minus 2 over 3, so think about that over there, 5 over 3 minus 2 over 3, we're subtracting the exponents because the bases are the same. That's just equal to 3 over 3, and that's just equal to 1. So that's just 2t to the power of 1. So that cancels, and this just becomes 1, and that's how we ended up with our exponent there. All right, so what we have to do here is we have to set s at t is equal to 0. So 0 is equal to t to the power of 2 over 3, and then 2t minus 5. Well, that leaves us with two possibilities. T could be equal to 0, or t could be equal to 5 over 2. That's our other possible value for t. Note that this one we're going to discard because this is the initial time, right? And so this is when it returns. Okay, again, so if I want to find the magnitude of the acceleration at the instant it stops, okay? So if I want to find the instant it stops, the first thing that I'm going to have to do is find v at t, set v at t equal to 0, because recall, that's the instant it stops, the velocity has to be equal to 0. Once I have that t value, then I can sub that into the acceleration function. So again, I'm going to find the velocity function. I'm going to set it equal to 0 because the object has stopped. Once I find that t value that causes the velocity function to equal to 0, I'm going to input that t value into the acceleration function. So the first thing that I'm going to do here is I'm going to find the velocity function. So the velocity function, recall, is simply the first derivative of the position or displacement function. So if I go up here, I'm actually going to take the first derivative using this function right here, not the factored form. It's easier to take derivatives of unfactored expressions because you can take advantage of the power rules. Yeah, we can go ahead and just take the derivative of this function to get our velocity function. Okay, here it is. I brought the exponents down and subtracted by 1, so I used the power rules, and then I cleaned it up a little bit. Now what I have to do is I have to find when does the velocity function equal to 0. All right, so if that's the case, again, if this is my velocity function right here, it's hard to find it equal to 0 when it's not in its factored form. So the first thing that I'm going to want to do is I'm actually going to want to factor this right here. And I look and I see that it has a common factor of 10 over 3, so I'm going to put 10 over 3 right here. And then I look for the variable with the lowest possible exponent. So the lowest possible exponent is t to the negative 1 over 3. And then I get t minus 1 right there. If I wanted to rewrite that, that's 10 over 3 to the cube root of t minus 1. So I can see immediately, first of all, that t cannot be equal to 0. But the answer that makes this equal to 0 right here, so therefore t is equal to 1 when v at t is equal to 0. So if I set this equal to 0, the only possible value is t is equal to 1. Okay, so now that I have t is equal to 1, I'm going to input that value into the acceleration function. So in order to find the acceleration function, I just need to find the first derivative of the velocity function. Again, recall that it's easier to take first derivatives of unfactored expressions, typically, not necessarily as a rule, but it generally, I find it a bit easier to find derivatives of these functions as opposed to their factored forms. Okay, so here's your first derivative of the velocity function right here, and this is it cleaned up right here. So recall that what we're going to do is we're actually going to find a at 1 because I want to find the magnitude of the acceleration. I'll just scroll up here. I want to find the magnitude of the acceleration of the object at the instant it stops. Well, I know it stops at t is equal to 1, so I'm going to sub 1 into this right here. And so I'm going to go 20 over 9 and times the cube root of 1 plus 10 over 9 times the cube root of 1. Well, I know that the cube root of 1 is just 1. So this just equals to 30 over 9, which I can say approximately equals to 3.33 meters per second squared. Let me just verify that my units are correct here. Yep, displacement is in meters, t is in seconds. So the magnitude is 3.33 meters per second squared. Okay, this is going to be the last example we do for this video, and then the next two examples I'll do in a separate video. A projectile is fired upward so that its height after t seconds is given by h at t is equal to 40t minus 4.9t squared, where h is in meters above the ground. So I've got h in meters and t in seconds. Okay, so this is just projectile motion. Determine its initial velocity. So what I'm going to do is I'm going to find v at t. Okay, so let me find v at t. V at t, recall, is given by the first derivative of the position function. So v at t, taking the first derivative of this position function right here, is equal to 40 minus 9.8t. All right, so if I want to find the initial velocity, what I'm going to do is I'm going to set t is equal to 0. So v at 0 is equal to 40 minus 9.8. T is equal to 0, so v is equal to 40. And so I get 40 meters per second. It's a positive value, so positive value meaning that it's being fired upward. Okay, so I found its initial velocity. Determine its maximum height. So its maximum height is going to happen, right, when v at t is equal to 0. So you might think, well, why is that the case? Why is the maximum height when it stops? Well, recall that if you fire something upwards, right, it's going to go upwards like this. And then when it's at its maximum height, it's going to stop instantaneously before it then goes back down. So I'm going to find the velocity when velocity is equal to 0. So 0 is equal to 40 minus 9.8t, and I'm going to solve for t here. So then negative 40 divided by negative 9.8 is equal to t, and t is equal to 40 over 9.8. So what I've just found right there, that is the time when the object stops, right? And so that's the time when the object stops, therefore at max height, as I just said over here. Okay, so if that's when the time when object stops or it's at its maximum height, I'm going to insert this time value into my position function. So that's my position function right there. I'm going to insert the time value 40 over 9.8 is equal to 40 times 40 over 9.8 minus 4.9, 40 over 9.8 all squared. Again, if you're curious where I'm getting this function from, that's just the original position function, right? I'm trying to find the maximum height, and I'm using the t value when the object stops when it's at its maximum height. So what is that height value? That height value is approximately 81.6 meters. And then it says determine its acceleration. Well, acceleration is pretty straightforward because acceleration is just the first derivative of the velocity function. So if I have my velocity function, which is given by 40 minus 9.8t, then my acceleration function is given as, okay, well, the first derivative of 40 is 0, and the first derivative of negative 9.8t is just negative 9.8. And that's negative 9.8, and that's meters per second squared. Again, this makes sense because this right here, if it's projectile motion, right, recall, one second, this would be the acceleration due to gravity for projectile motion. That's acceleration due to gravity on Earth. Okay, so that's where we'll stop for today's lesson. There's two more examples. They're very specific examples and they're very similar to each other. So I'll cover those in a separate video. Thanks again for watching.